Right. So my first thought, formalization, instead of presenting, I could have presented a formalization where in mathematics now, you're formalizing something a month after the preprint has appeared. In computer science, you do it at the same time as you're inventing. And in particular, I could have presented something if you add to a symmetric rig groupoid the square root of naught and the 8th root of the identity scalar and the 3-braid equation, you get a universal quantum programming language with a sound and complete reasoning system. I could have, kind of assailed you with that stuff. And I chose not to. But if you're interested, talk to me. I'm going to try instead to entertain you with some, basically going at the absolute opposite end and looking at really, really simple stuff and seeing the mathematics that comes out of that in a sort of inevitable fashion. Now, if we think of universal algebra, leaves this, and category theory, I won't spell it out, as the fundamental language of meta-mathematics. So if you want to talk about theories, you're going to be using all of that language. And so I'm going to take as an axiom that these are kind of part of the infrastructure of math. Okay, so let's, and the way I look at formalization is I tend to be extremely systematic. I'm extremely interested in building large libraries and not just of interesting mathematics, but kind of everything that's supposed to be there, no matter how trivial. So let's start at completely trivial. I'm going to treat a theory. Which way should I go with it? Right. So let's take a look at the theory of pointed types, just in my method, so I don't confuse my notation all the time. So we have a type, and we have some point, let's not call it that, some point in A. Right, so as trivial as you can possibly get, like, if you don't even have a carrier, it's not interesting, fine. First thing, lowest possible arity, do that. Great, that's so boring, it's just not funny, right? Well, you'd start turning the crank of category theory, so the first thing you think of is, of course, I need a theory of the homomorphisms of pointed types. And you're going to have two of them. That also gives you a type. Some function from the carrier of A to the carrier of B and A, and it preserves your point. So f of x dot point is y dot point. Right. Sorry. But it's useful for me to write it out because I'll color all sorts of things. Then you show that the homomorphisms compose. There's an identity, so you have a category of pointed spaces. Great. Then you notice, because you know where to look, that there's a forgetful functor from the category you've just created out of this to the category of just spaces, and you know what you should be looking at. Oh, it has a left adjoint. So there's a free pointed space. Go too big. Yeah, all right. And on objects, you end up doing x is 1 plus x. As you basically invent a new point, and then of course you know that this gives rise to what is often called the maybe monad. Just by the act of writing down this theory, all of that is free. Right? It's turned a crank. If you view this as constructions that are free, the computer can derive all of that for you. You've written down something ridiculously trivial, and by the time you've gotten to the maybe monad, you have the basics of partial computation in computer science. Like the fundamental infrastructure is already there by writing something this trivial. So,
Can the computer find the adjoint for you?
No. This is a theorem. This is a theorem, but that is the theorem is effective. So once you prove that theorem as a mathematical thing, now it's free.
Yeah. Okay, but you need to develop quite a lot of.
Yeah. But so once you've done enough meta theory, then a whole lot of your theory is free.
And does it not use the maybe monad?
You end up discovering other things that is not used. And indeed, right? Like, not everything is free, but because in some sense, if you took this as an axiom, that this stuff is, and then you go back to look, and there's interesting stuff from completely trivial things. So if we do it again, instead, yes?
I'm sorry, I don't understand. How is the maybe monad less trivial than the pointed type theorem?
So the forgetful functor from the pointed theory to the theory with just a carrier, the left adjoint to that is...
I understand this left adjoint stuff, but I mean, what I don't understand is the claim that the maybe monad is less trivial.
No, so the like left adjoints induce a monad.
No, he's asking why is the maybe monad non-trivial as a concept compared to pointed types?
Why does it make your life easier to have the maybe monad? I think
It feels like the maybe monad comes out of thin air. Like once, of course it's trivial, but like I'm going to show you other things that also come out. Like I wanted to start somewhere where it's completely easy to understand, and I'll complicate bit by bit. So the maybe monad is still trivial, but if all you have in your back pocket is like the very basics of category theory, the super basics, and universal algebra, you might be surprised that the maybe monad comes out. Don't think of
Well, it's a background issue. For me, category theory and universal algebra is much more complicated than the maybe monad.
Sure, of course. Yeah, but like it's infrastructure. It's in your meta theory, and I'm looking at it from the point of view of developing a system and what should come out for free.
This is one example of a general thing.
It's one example of a general thing. Yeah.
Isn't that the point? So does that answer your question? Yes, and maybe the one example is simpler than the general theory. Is that what you're saying? It's true. But I think the point is that there's a general theory and lots of things will follow from that. And this is an example. So it means the theory applies to.
We should wait for more examples.
Right, so the next thing you think of is instead of having arity 0, you go with arity 1. This is, so you still have to type. And then you have a homomorphism, and you use look at the forgetful function, like you have the forgetful functor, it does have a left adjoint because all of these do. And you get something that, as far as I know, doesn't have a name. And on objects, you can either see it as mapping applied to S for S, some new symbol. You shouldn't perhaps use S. Or you can see it as mapping to pairing with a natural number, and like for some natural number. And this basically, it's kind of like the delay monad, not the delay comonad, that you typically get for streams. And it's basically related more closely to the idea of fuel in total computation, where people often think, hey, in total programming languages, it's not Turing complete, blah, 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 you can't do anything. Well, actually, that's not true. If you use an exact fuel monad, then in fact, you give fuel to a computation, it uses up that much. If it terminates, it terminates. If it doesn't, you just need more fuel. And every function can be put this way. If it doesn't terminate, well, you needed to put in infinitely amount of energy. You've pushed the problem to the consumer side instead of having unbounded recursion. Yes? At the back first?
Do you need an additional term to get this to natural number?
So the natural representation is this, but you can prove that it's equivalent to that. Modulo laziness versus strictness. So if you're strict, then there's a problem with the empty type. But
I think the remark I was going to do answers that question. It's like, so this free construction is like the natural numbers, except you replace 0 with the numbers of S. So if you replace the 0 by
an actual payload.
This is like, actually the dot is then something else.
Yeah, the dot is kind of a pair. I should probably say it's a pair, but it's kind of a strange pair because you're not allowed to look at the X unless the N is 0.
Okay.
So it's a, yeah, like that's the type of it. Sorry. And then we can do, at this level, one more magma. And then here we add, say, an operation that we'll write in fix. And we do the same thing, and over here we get binary trees. It just, boop, there we go. And binary trees are like super fundamental to computer science. And you know, when you take a look at the first 3 kind of most trivial theories we can think of, out the other end already comes out interesting stuff. Right, okay. But, so universal algebra teaches us the interesting homomorphisms are the ones that preserve everything. But why not? Like, why do we have to do that? What if we don't? So we go back to our pointed theory and say, well, what if we look at different homomorphisms of pointed theories and not preserve the point? You get a category, you get a forgetful functor, it has no left adjoint, it doesn't exist. the theorems from universal algebra really, really care that you preserve everything. Forget something, it doesn't work. Interestingly, if you get that process, what category do you get? You get the category of inhabited spaces. The category of inhabited spaces has kind of been defined only about 30 years ago. People weren't even looking at it, and it was defined through a truncation operator and all sorts of really fancy stuff. But roughly speaking, using knowledge available around 1942 or so, the category of inhabited spaces could have been defined. And nobody saw it, because nobody was looking. And that's the first part where I find the most interesting, that by systematically looking at this stuff, you get things that are kind of newish. There's no left adjoint also with magma, and I don't know like a category with some kind of free, like some kind of binary operation that exists, but you can't pin it down. I have no clue what that is. Like being inhabited, I have a clue. The other here. Now, I haven't worked out all the details, but UNAR is interesting because there is always a distinguished, free unary operation. It's the identity function. So you always have that. So I need to dot the I's and cross the T's, but I'm pretty sure this one has a left adjoint, but it's trivial. Yes.
So you're saying you take the same objects, but your morphisms are not always just the morphism of types.
So right. So for pointed, you same objects, but you forget this in the theory of in the homomorphisms.
But it's always a full subcategory of this.
All of these things end up being categories.
No, like always a full subcategory. Right?
Sure.
Like it's fully faithful inside the thing you start with, and you're just trying to figure out which objects now live inside the. Right? Is that a question?
But basically, in the pointed case, this works even when, it's because you're able to name a point versus you know it exists, but you have no name for it. So there's no way for you to get your hands on it, and this gives you problems.
That's what I say. It's a full subcategory of.
You want to determine which objects came from the image of these.
And you can't.
Which types come from the image of these constructs.
Anyways.
The identity works out. Magma does have two canonical members, true and false, right?
In magma, that's a binary operation.
Left and right projection.
So,
you can forget.
So you have true and false. Projector second. From the first argument, projector the second.
No, you have no points here, right? You don't even know you're inhabited.
You don't need.
It's still a function.
Yeah, there is. Okay, so I have.
X y to x or x y to y.
Yes, and
Will you get some?
Yeah, it's worth poking around. I haven't poked around that particular hole. Let me poke around somewhere slightly different. Yeah, well, that's great. So if we look at the free pointed type on the empty type, let me write it this way. Then this has one, it's equivalent to 1 because you're adding 1. And free pointed on 1, like the two things you always want to try out is on the empty type and the type with a single thing. So you get back, but the interesting thing here in some sense is already you get the 2, or booleans show up. Because they're apply free unar to empty because it's not pointed, you get empty. Same with free magma. Here, if you go for 1, then from this representation here, you get the natural number, and here, if you go for 1, you get the hereditary hereditarily finite binary, which are equivalent numbers. So hereditary finite sets actually kind of show up really, really early on as well. It's kind of, you just try out stuff, and all of a sudden something that seems complicated, by just saying I've got a binary operation, you turn the crank, and these are already there.
What's a hereditarily finite number?
Sorry?
What is a hereditarily finite number? I think
It's basically a finite tree. It's usually seen as a set of sets.
that I know, but that's what
Yeah.
you call it a number. It's just
But okay, set.
no, that's okay. It's just
But like once you have unit at the bottom, then it's always equivalent to a number.
Okay.
Different number
I
representation.
understand.
So, of course, the next thing to do is I stuck to the language of universal algebra, single sorted equation, blah, blah, blah. And so one of the things you might want to do is generalize your vocabulary a little bit to allow more stuff in your theories and see what you find out. Of course, if I keep turning this crank, ternary, and then I turn the crank some more and I have both a point and a binary operation, and it gets more complicated, but quickly you don't find anything all that interesting. You will find interesting things again once you add axioms, right? I've done things that are completely, in some sense, really boring because I can't even have a monoid. What the Haskell people call monoid is really pointed magma, and it's really, really annoying that they call it monoid. And pretty much all the poor programming languages call something monoid when it's really a pointed magma. So if we add a strange law, if we add associativity to magma to get semigroup, what we get out when we turn the crank are non-empty lists. They just come out. Of course, as we know, if you do monoid, then you get lists. If we add for all x, y, k, whatever some binary operation, x times y, you always simply forget what the x is. You still get a monad structure on your magma, and this is actually sometimes called the last monad, which basically, when you're fed stuff, you keep the last thing. Of course, if you do x times y is x, then this is the first monad. You keep the first thing. And interestingly, if you build these on semigroup or on monoid, you add these to, you actually get quite different monads that behave differently, that are both useful. And these are really at the very, very low end of how many things you have in your theory. And these are defined in the Haskell standard library, for example. I was kind of surprised.
So just to clarify, I guess, when you were doing this, you weren't just generating types, you were generating types with the monad structure?
I was, like
Like when you write down Sn times x and so on, you're not just talking about a type. You're talking about a type with a monad structure.
I'm talking about, yeah. So you get, like, you need to get the full structure. Don't have time, but yes, the forgetful, sorry, the adjoint generates like a full theory that has a whole bunch of kit. So you don't get just a type, but it has
what structure does it? I actually don't know what structure should I expect out of these three things. Like I thought we were just going for sets, but I guess
yeah. So you just go to set, right? So the maybe monad is.
I mean, it's not just what I mean. It's not just option. It's the monad.
It's the monad. It's
the
monad of option. So first you get the left adjoint, and from the left adjoint you get the monad.
And the monad laws and
the monad laws, and you get everything.
Okay.
And the fold, and like the co-unit is fold. You get all the kit, and the fact that back and forth behaves the way you want it. And it's just there,
and so here, when you're generating, you don't get a new step, but you get a new operation on the set.
You get, yeah. So those are kind of neat. Now, something breaks at some point, where in universal algebra it's all fine. Axioms like for all x times x is x, i.e. idempotence, or commutativity. Now, the classical mathematician is still super happy because everything keeps working. And the constructive mathematician is very unhappy because now the things that you get don't have normal forms anymore. And so from a computer science point of view, some of these axioms are horrible. You can't work with them. So there's, in fact, a whole area of study around regular categories, like regular theories, which basically says the shape of your axioms matter. Roughly speaking, your axioms need to be linear and use their arguments in either, it doesn't have to be, okay, it can be affine, it doesn't, but have to use their arguments in the same order they came in. So if you view it as something from consuming things from a context, then they have to be consumed in the same order that they were given to you in the context. And those always have normal forms. So from a computer science point of view, those are nice. The other ones need more work. So of course, the one we like the most, how much time do I have left?
So 9 minutes, including questions.
Including questions, okay. So the one that has seen a whole lot of papers by very famous people of late is BAG, i.e. Free commutative monoids, because they have no normal forms and the amount of kit you need to deal with those is enormous. And part of the issue is this issue that commutativity as an axiom has the wrong shape. It is it swaps things around.
free commutative monoids are bagged.
Yes, free commutative monoids are bagged.
And sort them, you have no normal.
Right, and so either you assume that the things you put in your bag have a decidable equality, at which time everything's fine, or now you need to work harder, whether you use homotopy type theory and hits or this or that. There's a whole bunch of different technology. But the interesting thing is everything up to now didn't need that at all. It works constructively and not in the exact same way. And to even phrase free commutative monoid properly, the theorem prover, you need to have what I like to call a programmable equality. The forgetful functor doesn't go to set or type, it goes to setoid, because it allows you to change your equality the right way so that you can quotient. And you're forced to do this because otherwise you can't even say what equivalence relation holds on your objects. So it's kind of interesting that as soon as you have kind of non-linear axioms, you must be able to say, I'm actually going to setoid because I'm going to program my own equality. There are other ways, right? Hits and like there's like 3 or 4 different technologies you can use, but you must start using something else.
Yeah, I was going to ask you, quotients, I know.
Yes, if you have quotients, that works too, but like it depends on what you've baked in. But the point is you must use something else. You can't just do something. Right, so if you go to 2-sorted theories, then you get left and right actions and graphs coming up naturally in interesting ways. If you're also 2-sorted, then you start looking at, instead of merely adjoints to the forgetful functor as being interesting, adjoints to the diagonal functor become very, very interesting. And then you get sigma types and pi types. Those just come out naturally as being there. Right. And then I will finish here. If you go to dependent types, type where we have some shapes, type, and some positions types that depend on S. So once you change your vocabulary to allow dependent types, and you start enumerating your theories, this is one of, in almost all enumerations you can think of, this is one of the first ones that come up. And these are containers. And over here, the homomorphism type that you get is lens. So lens are super hot in certain areas of computer science right now, have been for 15 years, and they're just the homomorphisms of containers. There's 2 kinds, whether you want Cartesian lenses or not. So you get an option on your homomorphisms again. But like, if one had been systematic about looking at these things, then as soon as the dependent types are out and you just look at the homomorphisms, lenses could have been discovered much, much, much earlier, because they're just here. And we don't quite know as we keep doing the rest, because basically we've gone so far out of the realm of universal algebra and category theory. I'm not sure anybody's really looked as you know, what keeps going. Like, what are the other 3 things that you ought to get? Yeah, I don't know. But to me, it's really interesting that, like, looking at the basement of theories and just turning the crank, all sorts of fun stuff comes out. I'm done.
Thank you.